Okay, let's get going. Before we start talking about the stuff for STEM language, are any questions about the multi-level homework assignment for Thursday? Some questions in office hours, but if there's any others that haven't been answered, the difficulty I think some people have had in thinking about the model is what this delta comes from, which is the unknown, but it's specific to a particular study. So one way to interpret that, I think, would be some characteristic of the research design that makes it more or less appropriate for estimating the true parameter mu. So there's like normal distortion in research designs, and then for a given research design, you have just like random people or whatever in your study, and so there's going to be further noise in that, which is captured by these observed estimated standard errors in each of the studies, and that's another aspect of the problem. But thinking about delta as an unknown and y as exogenous or observed but endogenous, and y being the estimate that comes out of the study. And then thinking of the observations and meta-analysis as a study that could be grouped further by authorship and things like that. But anyway, so once you get a sense of what the deltas mean, then just translating it into a prior predictive distribution is relatively straightforward, but its prior is going to depend on other unknowns. So that's what makes it multi-level. Any questions about that? Okay, so today we're going to be starting, even though it might not seem like an actual start, talking about the STAN language, in which case we should remind ourselves that being at Columbia being very engaged in trying to get grants about STAN, teaching these sorts of things while also using STAN outside of Columbia creates the appearance of a conflict of interest that you should be aware of. And so in the previous weeks, we've been talking to a greater or lesser extent about STAN, as opposed to sort of general ideas about Bayesian inference. And sometimes we did a short STAN function, but starting this week, we're going to be learning to write entire STAN programs. But hopefully, based on the experience that we've had so far with writing functions in the language, it won't seem like such a big step or a jump. But really, the reason why I have to go quickly through all the material we've gone through quickly so far is so that we would have these last 3 weeks of the semester to talk about writing your own programs in STAN as opposed to just using RStanArm and which comes with STAN programs, and VRMS, which generates STAN programs locally on your machine when you call VRM. So a different way of designing a class like that periodically I think might be better for a wider number of people is, okay, well, we could stretch every 4 days that we did previously over 5 and just sort of end this semester with using BRMS and estimating multi-level models, and not try to tackle the additional step of writing your own programs in the STAN language. But I think that would not convey sufficient sense of what the programs underlying RStanArm and BRMS are doing, or give you a sense of like how much more you can do if you write your own standard program. So like I said, BRMS by itself is roughly on par with some of the most general statistical programs out there in terms of how many models you can estimate. But if you start going beyond BRMS, writing your own STAN programs more or less by hand, you can expand what you can do by another several orders of magnitude. So that's because STAN is a general probabilistic programming language, and you can pretty much express any model that's differentiable with respect to its parameters in the STAN language if you know how to do so. And moreover, there's no like additional class that you can really take where you would learn these sort of things. So we have to try to squeeze it in this last 3 weeks, and so that necessitates going faster than maybe everybody would have liked through February and March and the first part of April. But anyway, here we are and starting to learn about how to write and estimate your own STAN programs. And so the workflow, we've talked about this a little bit before, but it probably wasn't so clear at the time. For doing things yourself in STAN is you write the program in a .stan file. And we know a little bit about the language already. It's somewhat similar to R and a bunch of other languages. And then STAN comes with a function that you haven't explicitly seen, but it's called stanc, and that does 3 things. It checks that your program is correct, or at least has the right syntax, and I'm sure you've seen the red messages that come up when you don't have the right syntax, sort of pointing you to the right line. And then once you get the syntax error sorted out, it writes a conceptually equivalent C++ file to your disk, and then it compiles that C++ file, which is what takes 30 seconds or so and often generates a whole bunch of not easily interpretable compiler warnings that you can ignore. And so once you have the C++, that enables us to use automatic differentiation, so teaching the C++ compiler about the chain rule. And so you, as the writer of the STAN program, don't really have to worry about any of this. But when you have, some expression like x is equal to mu plus sigma times z, like in a normal distribution, C++, in addition to calculating x, can store the derivative of x with respect to mu and sigma and z. And if x was part of some other calculation, automatically handle the chain rule. So you can get the derivatives of the posterior distribution with respect to mu and sigma and whatever. And that is known as automatic differentiation. And STAN, as we'll see in a second, it has this distinction between data which is known and unknown parameters, etc. And so if one of those things, any of those things are a constant, then STAN knows it doesn't need to differentiate with respect to that. And so that's why we make it into C++ to hook into math library that knows how to do automatic differentiation with respect to unknowns, so that people don't have to worry about that and risk making mistakes. And then once it's compiled, the C++, the binary gets loaded into R, and then it can be executed. You actually see like all these steps mostly done concurrently, except for the part where you sit down and write the STAN program. But after that, it's sort of all looks like one step. And then when you get the draws back from the posterior distribution, you analyze it, and that's what we've had a fair amount of practice with, really the end part, with RStanArm and BRMS. However, the difference is when you write your own STAN programs, R knows nothing about what those STAN programs were about, whereas in BRMS and in RStanArm, there's sort of like a R representation of the model and a STAN representation of the model, and so we could do more automatically after the fact because the R functions know what the model was, whereas that's not the case if you do things by yourself, but you should know what the model was. If you wrote it in Stan and you understood what you wrote and you wrote what you thought you understood correctly, in which case it's not too much of a burden for you to do some of the things afterward that were sort of handled automatically by RStanArm and DRMS. So this we mostly know already based on experience with homeworks and stuff, but in Stan, because it's compiled into C++, has a lot of the same characteristics. So when you declare a variable, it has to be declared with a type in addition to just a name. The names can have numbers, letters, and underscore, but can't start with a number. Statements are terminated by semicolons, and so they can run over multiple lines. The basic, most primitive scalar types in Stan are the real numbers and the integers. Those integers are signed, even though often it doesn't make sense to have negative numbers, but that's possible. Remember that when we do stuff with Hamiltonian Monte Carlo, the unknowns can't be integers because Hamiltonian Monte Carlo requires the posterior density to be differentiable with respect to the unknowns, and you can't differentiate with respect to an integer. However, you can condition on integer data, whether that's the outcome, a predictor, something else, because no derivatives are needed with respect to constants. We only need to differentiate what the posterior distribution is a function of, and it's a function of the unknown parameters. So vectors, row vectors, matrices, etc., those all implicitly contain real numbers, or they're going to store them as real numbers, which is to say double precision, even if they happen to be have integer data in them. Stan distinguishes between a vector and a row vector. So by vector, we mean column vector oriented up and down, row vector oriented horizontally, but those are technically different types in the Stan language. Moreover, Stan distinguishes between a vector of size 1 and a scalar, even though a vector of size 1 only contains one number. That's in contrast to R, which doesn't even really have a notion of a scalar. It just has length 1 vectors. But Stan distinguishes between those two. Matrices also implicitly contain real numbers. They're going to be stored as numbers, double precision numbers. You need to specify the number of rows and the number of columns, as opposed to a vector where you just need to specify its size. You can have a matrix that only has one column, and you can have a matrix that only has one row, and mentally those are like vectors and row vectors, but they actually are different types in Stan. And so if you know that this thing only has one column, use vector type rather than matrix type with one column. But you'll see, you know, if we did like a regression, you might want to declare a design matrix X, but in general, X has k columns, but in any particular case, you might only have one predictor, in which case it would be an n by 1 matrix, and that's okay. It's just if something only has one column, it's a bit more efficient to represent it as a matrix vector than as a matrix with one column. Arrays are sort of other containers that can contain anything that all has the same type. So an array in Stan is much like a list in R, with the restriction that all of the elements of the list are the same type and the same size. So unlike a R list, which allows, you know, you can have a list of anything. They can be heterogeneous objects, different sizes, etc. So you can have a real array called X of size n, and mentally that is similar to a vector of size n. However, if you declare it as a real array of size n, one, the n goes after the x as opposed to after the r in vector, but that's not that fundamental a thing. The vector has linear algebra properties associated with it. So you can multiply a matrix times a vector and get like matrix vector product. The real array of size n is really just storage. It doesn't have any linear algebra concepts associated with it, and thus you couldn't multiply a matrix with n rows by a real array that has n elements to it. That will result you in a syntax error, but you could do it if that was like a row vector. So my basic advice is don't use real one-dimensional real arrays, just use vectors. And don't use two-dimensional real arrays, just use matrices. But if you have like a three-dimensional, four-dimensional structure or whatever, then you would have to use a real array for that. I think you can do up to like 6 dimensions, which is enough for anybody. But arrays don't have to just hold real numbers. You can have an array of anything. So you can have here in this expression, I've declared an array named x. That x is going to have k elements. Each of those elements is a vector of size n. So if this was in R, I would have a list. The list would be named x. The list would have k elements. Each of those k elements would be a vector of size n. And you might say, well, is a real array with k elements that each are a vector of size n, that's like a matrix, or more specifically like a data frame, maybe, in R, whose columns are all numeric. And so for the most part, that's just a confusing way of specifying a two-dimensional structure, but this does have its uses. So if you need to do something in your STAN program referencing the columns of a two-dimensional thing, it can be more memory efficient to declare it as an array of size k, each of which is a vector of size n, if you need to refer to it column by column, because the vectors are stored in contiguous memory. Whereas if you declare it as a matrix of size n by k, the columns are not necessarily going to be in contiguous memory, and it's not as easy to reference them by indexing. But that's really just a performance thing. You could get it done with a matrix. Another way of representing a two-dimensional structure would be to declare an array named x that has n elements. Each of those n elements is a row vector of size k. And so if you needed to do something that referred to entire rows of your data set, then row vector k x n might be a more efficient way to store and access those things by rows than would an n by k matrix. So all three of these vector of array x k elements, each with a column vector of size n, or x with n elements, each of which is a row vector of size k, or a matrix with n rows and k columns, all refer to two-dimensional structures that contain real numbers that have slightly different uses. But if you need to loop over the rows or the columns, one of those may be more efficient than the others. But again, we're really only talking about performance gains here, and only probably with very large data sets would you even notice those. But you could also have an array of, with p elements or something, each of which is a matrix with like n rows and k columns, etc. So think of these arrays like lists in R, but they all have the same thing as their elements. Questions about that? Okay, so I said before that vectors and matrices are going to store things with double precision numbers. So if you need to use integers, and you often do for the outcome variable, so if the outcome variable is discrete and you want to use like a Bernoulli or something, likelihood that is only going to be defined for integer arguments. And so in that case, you actually need to be storing the thing with integer types, in which case you can use a one-dimensional, two-dimensional, six-dimensional, whatever integer array. Int y with n elements to it, or n elements and p elements on the second dimension, etc. So multi-dimensional integer arrays definitely have a purpose. Storing an array of vectors, an array of row vectors, kind of has a purpose, but you can get away with just using a matrix. Using a one-dimensional real array basically doesn't have much of a purpose, but it is valid syntax. It's just sort of a less functional version of a vector because it doesn't have the matrix algebra stuff associated with it. But if you need something to particularly be stored as integers, you need to use integer arrays of however many dimensions you need, rather than matrices or vectors, etc. All right, so we've come across, I think, most of that already. Also, I think I mentioned this before, but then I got to thinking I couldn't remember when I mentioned it. There's a function in RStan called Lookup, where you can put in the name of our function and it will try to give you back the name of the corresponding stan function, or you can input a regular expression and it'll find stan functions whose names match that expression. So if you put in like starts with inv but doesn't end with g or f, you get back all these stan functions, and it says what are the arguments to those functions, what is the type of the return of those functions, and at least for now, it still refers to the page number of the PDF version of the Stan reference manual. The Stan reference manual is basically well along into going to HTML, so we'll probably try to replace those with HTML links to those functions. But in any event, if you know what you're doing, it's often sufficient to just like look up the function to know what the order of the arguments is and like what type of thing it refers to. But if you need more information, then you can always refer to it in the Stan functions reference manual. Also remember, in Stan, like in C++, you can't specify arguments by name like you do in R and like you should do for the most part in R. So all of the functions that you call, the arguments have to be specified by position. And so that is the cause of a number of bugs putting the arguments in the wrong order when you're calling a function. So you need to make sure you know what the signature of the function is when you are trying to call it. But having this lookup table makes it easier if you sort of know what the function would be in R to figure out what the function to do the same sort of thing would be in Stan. So the Stan, a whole Stan program, as we'll see in a second or later on as we go today, consists of a number of blocks. And so the only block that we've been dealing with so far is the functions block, which is actually optional, but you can use it to define your own functions in the Stan language. This is useful for a number of reasons. One, you can write one function and you can use it in a variety of Stan programs. Having these small functions with informative names can make subsequent chunks of your code more readable by sort of separating out the details of how something is calculated and being able to sort of understand the story of the stand program just by looking at the names of the functions you're calling. It allows you, we certainly haven't done anything along these lines yet, and we probably won't this semester, but it enables you to define posterior distributions that involve so-called higher order functions, like doing an integral or solving a system of ODEs or solving a system of algebraic equations, or some other stuff that involves like optimization or root finding or something like that. You have to define the function that you want the integral of before you can call like the integrate function in stand. So by having our own functions, you can do posterior distributions that involve higher order functions. What we've mostly been using it for, and it's also very useful, you can export those functions to R using the exposed stand functions. So you can call them, you can check to make sure they're working correctly, you can check that it yields the same answer as a function that you have in some other R package that is thought to be correct, etc. But then, as we'll see today, we can actually use those functions within the stand program rather than, or in addition to, exporting them to R, which is all useful. They have to be called by position rather than by name. I've said that there are no default arguments for regular functions, so all of the arguments have to be specified, and obviously you can't have two functions with the same name, can't have a function that's the same as a C++ keyword, things like that. The capitalization matters, just like in R, etc. So we're pretty familiar with that already, and we've used it to do things like this, where I'll write a 20-line stand function that does something like drawing from the prior predictive distribution on the left in black, and then I'll write another 20-line stand program that shows how to evaluate the numerator of Bayes' rule for that data generating process in log units. And we've been doing that to get practice for basically a day like today. But we'll practice it once more today, and then probably a few more times the rest of the semester. So we're going to kind of circle back to the beginning, or close to the beginning, and be doing relatively simple models, writing ourselves in the stand language and writing stand programs. So the first bowling model that we did on like the second day or whatever, we were using that probability mass function based on ratios of Fibonacci numbers, and it didn't have any parameters to it. And so that may have seemed a bit weird at the time. It was like, potentially applicable to like all bowler. Whereas if we use some distribution that had parameters to it, then we could estimate those sort of bowler specific parameters. And then, potentially we'd have a model that could be applied to a lot of bowlers, or we could do a multi-level model or whatever. So here is a data generating process for bowling that's going to involve a simplex of parameters, the probability of getting a strike, 9 pins all the way down to 0, etc. So the one on the left is how to draw from the prior predictive distribution. So we've done this a number of times, but this really represents what you think the model is. And this is something you really have to specify in order to indicate that you understand what's going on with the model, in addition to being able to evaluate your priors and other sorts of good things. So the exogenous unknowns are going to come in, the exogenous knowns are going to come in as arguments to that function, and then everything else the function can do for itself in order to yield back predictions of the outcome that's about to be modeled. In this case, the number of pins being knocked down on this or that roll of a frame of bowling. So this is going to return this function here is going to return a two-dimensional integer array. So this integer array is going to have like n rows for the number of frames the bowler produces, and 2 columns for the first roll and the second roll of all of these frames. And you would indicate that by having int with brackets and then a comma. So you don't have to say exactly what the size of the integer array is on the outside. You just have to say this is going to be a two-dimensional integer array. On the inside, you say, okay, it's int by 2. But on the outside, it doesn't matter. So I'm going to set up my draws integer array. It's going to have n rows for the number of frames, 2 columns for what happens on the 2 rolls of the frame of bowling. And then first, I'm going to draw from the prior distribution, which in this case is going to be Dirichlet, because I want a simplex vector for my parameters pi. So this is going to be of size 11. The elements are positive, and they sum up to 1. And so I can interpret this as like probability of a gutter ball, probability of 1 pin being knocked down, probability of 2, all the way up to probability of a strike. So the Dirichlet distribution is the most common one for parameters that are simplexes. So basically it's a PDF over PMFs. And it takes a vector of positive shape parameters A, which is exogenous known. For me, you could pass in any vector of size 11 that you want for A, and now we have a realization of this simplex vector pi that I can then fall into my loop for the number of frames that this bowler rolls, which is capital N, and I want to draw the data on those frames, the 2 rolls that go into it, conditional on my simplex pi. And this is what makes it different from the Fibonacci thing we were doing on the second day. Now we have a simplex vector of parameters, and potentially that simplex vector could differ from one bowler to the next, and so we'd have more flexibility there, more ability to use our model to say like this bowler is better than that bowler or something like that. But here I'm just thinking about having like one bowler who bowls like a bunch of frames, specifically n. So I drop into my loop over n. I draw the first roll of the first frame, x1, from a categorical distribution whose probability parameter is pi that I just drew from my Dirichlet. That's going to return me an integer between 1 and 11. And so I subtract it by 1 so that it's now defined on the sample space from 0 to 10, the integers. If that's a strike, then this frame is done. So I just stick in 10 and 0 into the row n, little n, of my draws two-dimensional array. I think I've used this syntax before, but if I haven't explicitly mentioned it, you can specify an array or part of an array with the curly brackets notation in Stan, separated by commas. And so my draws integer array has 2 columns. I put in 10 for the strike and implicitly 0 for the second roll of that frame, even though the second roll of that frame doesn't actually happen. But just, so I don't have any NAs or anything like that. But if it's not a strike, then the second roll of that frame happens. And so I'm going to need a conditional probability mass function for the probability of knocking down any subset of the remaining 10 minus x1 tens. So I define an integer that's n plus 1, which is just 10 minus x1 plus 1. And then the plus 1 is just accounting for the fact that Stan starts numbering at 1, but bowling starts numbering at 0 because you can miss all the pins. Anyway, so I have n plus 1, and I pull out a subvector of pi with the first np1 elements to it. So the Dirichlet distribution also has the property that subsets of a simplex, if you renormalize them, are 1 valid simplexes, but they're also Dirichlet. So I pull out the first NP1 elements of pi and then divide by whatever their sum is. Now I have a shorter simplex in general, unless the person got a gutter ball the first time, in which case it's just the same as the pi simplex that I started with. But in general, now I have a simplex, it's non-negative, it adds up to 1, but it only has NP1 elements to it, and so it's appropriate for my second roll of that frame of bowling, which I call x2. Again, I just subtract by 1 so that it goes from 0 to n instead of 1 to n plus 1. And then I stick x1 and x2 into the holder for the output for that frame and go on to the next frame and do it all again. And then at the end, I return back my invite to structure that has integers in it representing what happens on each of these rolls for all n of these frames by this bowler. And this bowler is sort of defined by his or her pi, which sort of represents his or her ability to knock down, more pins with some probability and less pins with other probability, etc. And so this is a simple, but not as simple as what we started with the second day, generative model for bowling. I've got my exogenous knowns, which is my hyper shape parameters that go into the Dirichlet prior, and then the exogenous unknown, the ability of the bowler to knock down a lot of pins, is pi. And then conditional on that realization of pi, I can get realization of observable data. And then I get back this thing at the end, and I can see if the distribution of predictions for pins being knocked down is consistent with what I believe to be true before I see the data on a bowler like this. And so we've got the exogenous knowns, we've got the endogenous unknowns, or endogenous knowns, exogenous unknowns, pi. And then they're used to generate the outcome, which is the endogenous known. There are no endogenous unknowns in this particular model, but in like a multi-level model or something more important than bowling, I might have a utility function or something like that I can evaluate over the prior. And so these prior predictive distributions really are your model before you see the data. And so you need to be able to specify a model, need to be able to understand a model. That's why we've been practicing these on pretty much every homework, but some people are still having difficulty setting one of these things up. But anyway, are there any questions about the STAN program on the left? Yes?
For the simplex pi, why use the class vector instead of class simplex?
Well, that's I guess too. Inside a function, you can only use like the basic types. So it is a simplex. It's non-negative and in sums to 1, but Stan doesn't like know that. So we'll see. Basically, in all the other blocks, you can be more specific about what things are. But inside a function, because like they get exported to R, they need to be like more vague and stuff like that. So anyway, but if it comes out of Dirichlet RNG, it is going to be non-negative in sum to 1. It's just you don't have the adjective there. Other questions? Okay, so once we've established a generative model, so generative meaning one you can simulate from, we have an ability to simulate pins being falling down. So then if we were to collect data on pins falling down from the wild, and this is our model, we can condition on the observed outcome data under that model to update our beliefs about the unknowns, the exogenous unknown, the ability of, particular, in this case, one bowler, but in general, multiple bowlers. So you have to set up the model first to say, okay, this is what I think of the data generating process. And if you have data that came from that data generating process, then you can feed that data in and get updated beliefs about the exogenous unknowns and any function of the exogenous unknowns you want to. But you have to have the model before, at least conceptually, before you get the outcome data. But once we have the model in mind, and now we have outcome data that we collected from the wild that we want to condition on, as opposed to this, which is generate predictions for what the outcome will be. Now, instead of using random number generation, we need to represent this in terms of densities, and in particular, log densities. So this function on the right in blue is the numerator of Bayes' rule that corresponds to this data generating process, but it's now going to condition on the bowling data that we have. And so now that becomes an argument to my function, this two-dimensional integer array, number of pins knocked down on the first and second roll by whoever this bowler is. And the numerator of Bayes' rule is a function of the unknown parameters, pi. And so I'm going to have a proposal for that, which is going to be the first argument to my function. And then I can evaluate the numerator of Bayes' rule in log units. So by taking the logarithm of a product, it becomes the sum of the logarithm, specifically the sum of the logarithm of the PDF for the priors, plus the log likelihood contribution from each of the frames, which is going to be our unit of observation in this thing. So I just initialize log like to be 0. That's going to be incremented by categorical log likelihood contributions. And I initialize log prior, or really just say what log prior is. It's the Dirichlet log PDF for the exogenous unknowns pi, given my shapes in the prior that come in as another argument to my function a. Okay, that's the logarithm of my prior. I'm halfway done. Now all I need to do is build up what is the log likelihood over all the frames. So I fall into my loop over the frames. Okay, the first one, I pull out the first roll of the first frame. That's x1. And since this is a categorical likelihood, the ex ante probability of that occurring is just whatever is the corresponding element of pi. So I index pi by x1 plus 1, because again, standard starts numbering with 1. But this is the log likelihood. So I need the log ex ante probability of that happening. So it's log of pi at the x1 plus 1 element. Okay, that's the log likelihood contribution for the first roll of the first frame. And if that first roll is not a strike, then I need to do the second roll of the first frame. So again, I set up MP1. Again, I renormalize pi in order to be a conditional probability mass function for knocking down between 0 and n pins, where n is 10 minus x1. Okay, now I have those conditional probabilities. I pull out x2 from my two-dimensional array of data, and I have another categorical contribution to the log likelihood, the log of the conditional probability of knocking down x2 out of n pins on the second roll of my first frame. And so those contribute to the log likelihood, and I go on to the second frame and the third frame, and I do all the frames. And then at the end, log likelihood has been built up for all of the contributions over all of the frames, and I just return back at the end the scalar, which is the sum of the logarithm of the prior PDF and the log likelihood, all the contributions for all the frames I observe. So this returns back a scalar, and this thing in blue, or something equivalent to it, is what Stan needs to know in order to draw from the posterior distribution of pi given the bowling data, which is sort of the basic thing that we want. Posterior distribution of what we don't know, given what we do know about the data that we've collected under the model that we've specified. So yeah, here we're drawing random numbers, our predictions of the outcome before we collect it. On the right, okay, assuming this is the right model, and we have data that we've observed that we think comes from that model, we can feed the data back in and get updated beliefs about the exogenous unknowns under our model, the posterior distribution of the unknowns given the known data. And so we sort of need to be able to do both sides of this, but in particular, we need to understand the differences between them. One on the left is before you collect the data, so predictions of the outcome before you observe it. One on the right is after you've collected the data, you need to specify the numerator of base rule in log units in order to tell Stan what posterior distribution does Stan need to be drawing from. But if you can do that, you can draw from any posterior distribution that is differentiable with respect to the exogenous unknowns. Questions about that? All right. So outside of the functions block, as Kyle was alluding to, you can declare any primitive object to have some additional restrictions, such as bounds. So if you have an integer for like the number of columns in a matrix or whatever, you could specify that with a lower bound of 1. So you can check if you accidentally pass it like -7, you'll get back an error message that says like this makes no sense because k is only meaningful if it's non-negative. Or if you have a correlation like rho, you can restrict it to be between -1 and 1 because that is an essential property of correlations that makes them unit-free. This lower bound and upper bound business doesn't just work for scalars. It works for vectors and row vectors and matrices and arrays thereof. However, the lower and upper bounds can only be scalars. So you have to be using the same lower and upper bound for all of these. If you don't specify an upper bound, it's implicitly infinity. So that's only violated if the thing is in A. But anyway, that works for vectors and matrices. Vector type has 4 different subtypes that you could use in addition to general vector. So unit vector is one that has the restriction that the sum of squares is equal to 1, but doesn't restrict the signs. Simplex, as we talked about a second ago, is going to be non-negative and add up to 1. So the square of a unit vector is a simplex. But simplex obviously has the further restriction that the elements have to be non-negative. You can have ordered of size k, in which case the elements don't have any particular sign, but one is bigger than the next. Or you can have positive ordered, which is like ordered, but there's a lower bound of 0 on the first element and consequently all the other elements. And so those are the 4 subtypes of vectors. But row vector doesn't have subtypes. So you can't have a simplex that's a row vector. Or you can define one, but you can't declare it that way. So it could happen to be a simplex. It's just not called a simplex. Anyways, unit vector, simplex, ordered, positive order, those are all, we think of them as vertical column-oriented things for the purpose of doing matrix algebra, if that's what you're doing. Also, there's 4 different types of special matrices. You can have Cove matrix of size k, because that has to be square, so like a covariance matrix like sigma. That's going to come and satisfy the restriction on its elements that it has to be positive definite. Better for most purposes, you can declare a Cholesky factor of a covariance matrix. Those are usually square, but they don't necessarily have to be. They can have more rows than they have columns in general, but usually it's a square matrix, so K would be the same number of rows as it has columns. So that is going to be lower triangular, and the diagonal elements are going to be positive. So L times L transpose is a covariance matrix that is positive semi-definite. You can also have a core matrix of size k. That's a correlation matrix, so it's also going to satisfy the positive definiteness restriction, but the diagonal elements are all fixed to be 1. Or you can have a Cholesky factor of a correlation matrix, which is also going to be lower triangular. The diagonal elements are going to be positive, and then each row is a unit vector. So the sum of squares along the rows would be 1 for each of those. That means it's a valid Cholesky factor for a correlation matrix. And all of these are particularly useful when we deal with multi-level models, which we're not going to get to today, but we'll talk more about on Thursday and next week. So all of these types are available to be used outside of the functions block. You can be more specific. Questions about any of those? Right. So the data block of a STAN program is more or less required. Technically, you could draw from some distribution and not condition on anything, but that would be like probably not very empirically useful. So the data block is basically all the things that you want to condition on in Bayes' rule. Everything to the right of the vertical bar on the left-hand side of Bayes' rule. So it's going to contain everything that's known, whether exogenous or endogenous. So that needs to be passed from R to STAN as a named list in R. So you collect everything. We'll show how to do this later, but you collect everything in R in a list. The list has names. The names have to correspond to the names of the things in the STAN program. And then you pass that from R to STAN to give STAN the data that you want to condition on when drawing this posterior distribution. So typical things that you want to condition on, and thus, pass from R to STAN would be like a vector of the outcomes, a matrix of covariates, the number of rows n, the number of columns k, things like that, in addition to hyperparameters like we had in the bowling model. A is the shapes that go into that Dirichlet prior. All of those are, except for Y, exogenous known things that you want to condition on. You can have comments. Well, you can have comments anywhere in a STAN program with either of the C++ styles. Unlike Python, white space pretty much irrelevant, although you do have to have white space around keywords. So anyway, a typical data block might look like this, although they're often bigger. But for like the bowling model, okay, we're going to have n, which is the number of frames. I've declared that with a lower bound of 0, even though it wouldn't make so much sense to have 0 frames, but as like an edge case, maybe that might be reasonable, but certainly having -4 frames of bowling would be a mistake. Then I have my x1, x2, an integer array with n rows and 2 columns. So I have to declare n before I can declare an integer array with n rows. These are executed sequentially. So if I did these out of order and did x1, x2 first, it would say, I don't know what n is. So n has to be conceptually, everything is passed at the same time as far as the human is concerned, but STAN reads it in order. So anyway, it gets n first and then says, okay, I have a 2-dimensional integer array of data called x1, x2 for the number of pins that fall down on each of n frames, and the elements of x1 and x2 are restricted with a lower bound of 0 and an upper bound of 10 in order to make sense for bowling. So this is the results of the number of pins falling down on each frame. Finally, I have a vector with a lower bound of 0 of size 11 with the shape parameters for my Dirichlet prior. All of these lower bounds are interpreted as weak lower bounds. So 0 is and 10 are obviously valid values for the data bowling. Also, technically, 0 is a valid value for A. So when you say lower bound, it's like lower than or equal to. And same with upper. Anyway, these have their curly braces, and that sort of defines the data block of the things we're going to condition on when utilizing base rule for this program that we're going to build up piece by piece. Questions about data block? Okay. After the data block, there's another optional block called transform data, which is executed only once, so before any of the MCMC iterations start, and you can use it to calculate any functions of the data that you need. So functions of exogenous knowns are also exogenous knowns. It's not super necessary ever to use the transform data block if you're calling this from R, because you could prepare all the exogenous knowns and whatever in R and using R functions, and a lot of times you'll find that easier. But stan technically can be used from Python, and it can be used from the shell, and it can be used from other situations in which you may not have all the functionality you need in the calling interface to set everything up. And so in that situation, the transform data block can be useful. It's also good for like presentation purposes if you have enough space. To put all the stuff or as much as you can into the stan program. That way when somebody's reading it, they don't have to flip back and forth between like the R markdown and the stan file in order to figure out like how all stuff was defined. You can just do it all in stan if you want to. Another thing you can use the transform data block is put in like print statements just to make sure that the stuff got passed in from R correctly. It'll just print out once what everything in the data block is if you want to. And you can check that those are things. So you can declare objects in the transform data block, assign to them using the equality assignment operator. The declarations have to come before the definitions, but it can all be on the same line. However, all declarations have to come contiguous to the opening curly brace. So I can have a block like this called transform data. I can declare a real scalar, which is the sum of the A's. And then if I wanted to, I can calculate the entropy under my prior using an expression I got from Wikipedia, which is just like this thing here. None of this was actually necessary for my model, but I just wanted to show how you could use the transform data block to do things like this if you wanted to. So just functions of like A, like that's fine. But you use the equality to assign them, and you have to declare their types. So you can sort of think of inside a block like transform data, it's kind of like being inside a function. Although you can use like the simplex type and other things like that, in which case it'll check that the thing that you say is a simplex actually is a simplex. And that's another way to avoid some programming bugs and mistakes on your part to declare things with the restrictions on them if those restrictions apply. Questions about transform data block? Okay. So the next block more or less required the parameters block, where you declare the exogenous unknowns whose posterior distribution conditional on the data is being sought. Technically, you can have a stan program that has no parameters, but then you're not really getting the posterior distribution of anything. So in general, this is going to have one or more parameters in it. You can't do any assignments within the parameters block, just like you can't do any assignments within the data block. You just sort of state the existence of whatever thing, whatever names you give to it. Like I said before, in stan, all the unknowns have to be real values. They can't have integer unknowns. And you need to declare the parameter space. So you can use lower and upper bounds. So like, variances or standard deviations need to have a lower bound of 0. If it's like a correlation matrix, okay, you're restricting it to the space of correlation matrices. If you don't specify the lower and upper bounds, they're implicitly plus or minus infinity, if that makes sense. But here I just declare a simplex of size 11, and so because I said it's a simplex that implicitly says it's between 0 and 1, all the elements, but moreover, they sum to 1. And so this is a valid probability mass function for knocking over pins in, frames of bowling. Again, I need this to be 11 in order to give me a probability of knocking down 0 or 1 all the way up to 10. So 11 things could happen on the first roll of a frame of bowling. So this parameters block is very short. It just has one declaration in it, but I could have more, intercepts and regression coefficients and other things like that in, different sorts of models. But all of these are customized to the posterior distribution you're drawing from at that time. So in this case, I just need a simplex. And okay, like I said, at one point in time, Hamiltonian Monte Carlo is going to be working in the real number, unconstricted number space. So it has to make transformations from the unconstrained real number space where it's doing the HMC thing to the constrained parameter space you may declare in your parameters block. And so there's a stick breaking transformation from real numbers to simplices of, in this case, size 10. That's sort of going on behind the scenes. And you say, okay, well, it's doing some transformation. That means I have to adjust by the determinant of the Jacobian matrix, or at least the absolute value, the logarithm of all that stuff that we did in like one 2x2 case, just so you have an idea of what that is. But that actually happens automatically. When you say this is a simplex, Stan knows the transformation that it needs to do. Hence, it knows the Jacobian of that transformation. Hence, it knows it needs to take the determinant of that transformation and the logarithm of the absolute value thereof in order to stick that Jacobian term into the numerator of Bayes' rule. But the good news is that you don't have to worry about that. Stan knows it's doing a transformation and it knows to do the determinant of that Jacobian. You just have to make sure to say this is a simplex rather than just like a plane vector. Because a plane vector with no restrictions on it, there's no transformation. So there's no Jacobian determinant, but then you would get numbers that are like greater than 1 or less than 0. And that wouldn't make sense in the context of a PMF for the number of pins out, down, and pull. So one of the mistakes that we see people make a lot when they're starting to define their own STAM programs is they don't define the parameter space specifically enough, with enough qualifications in order for Stan to know, like, what's going on. And they get standard deviations that are negative or whatever, and it shows up as an error somewhere else, and it's like you forgot the lower equals 0 on your declaration for the standard deviation. Here, simplex, okay, Stan knows how to do that. Then there is an optional transform parameters block, which is analogous to the transform data block, but it's going to be executed every leapfrog step as opposed to just once before all the sampling starts. Moreover, in the transform parameters block, you're evaluating deterministic functions of the parameters, although those functions can also involve the data. But the transform data block, because parameters hasn't been declared yet, in transform data, the functions can only involve data. But in the transform parameters block, which comes after parameters, after transform data, after functions, you can refer to anything above the transform parameter block within the transform parameter block. But other than that, it's like transform data. You need to declare the objects before assigning to them. You assign with the equality operator. This is where you can create endogenous unknowns that you need for like evaluating the log likelihood or something like that. You want to use the transform parameters block to declare and define things that you want to store the posterior draws of. If you don't even care about them, then we'll show another way to do that, in which case they won't get stored. If you have constraints and inequalities and qualifications, you should specify them because those constraints will be validated. However, if you know that the thing has the correct inequalities and whatever by construction. Like you have some real number and you do EXP of that number, you know it's going to be non-negative. And so if you don't specify the constraints, it executes a little bit faster because it doesn't have to check all of those. But if you have any doubt as to whether you've made like a mistake, I would specify the things with the constraints. That way you'll get error messages when your mistakes get exposed. I don't actually use the transform parameters block in this bowling model, so I don't have an example of it yet, but we'll see one soon. It's used more often with multi-level models to like define the group level parameters and things like that as a function of the population level parameters that you declare in the parameters block. So we'll see some examples of using that. The next block, also more or less required, is called model, which is a name that we subsequently regretted because the whole thing is kind of the model. But anyway, in the model block of a stand program, it's basically where you're saying, okay, this is what the numerator of Bayes' rule in log units is going to be. So you can declare and assign other endogenous unknowns, but they're not going to be stored. So this is just sort of temporary variables that you might need as intermediates in order to evaluate your log likelihood, etc. You can't declare constraints because they wouldn't get validated in the model block of a stand program. So you just have to make sure that the transformations and functions you're using are correct. Anyway, the model block needs to define something, or at least something proportional to the logarithm of the numerator of Bayes' rule. So again, we got prior PDF f of theta here multiplied by conditional distribution of the outcome given the parameters, and there can be also on x or whatever, but it's a function of the parameters. I take the logarithm of that, it becomes the sum of the logarithm of the prior PDF and the log likelihood. But the log likelihood can have a number of components to it, but sort of conceptually, I just have two terms here, even though they could have subterms within those two terms. So the logarithm of the prior PDF and the logarithm of the likelihood. So there's a reserve symbol in the stand language called target, which you get started out at 0 or started out at 0 plus whatever the Jacobian business that stand needs to do automatically with the parameters block. And then you just increment it for each of the terms in the logarithm of the numerator of Bayes' rule. So one for the prior, or if you have priors on a bunch of different parameters, then you're going to have a bunch of different increments of target, and then one or more increments for the log likelihood for the contribution of each of the data points to the log likelihood function of the parameters. Those increments are often going to involve calling functions that end in underscore LPDF or LPMF for log PDFs and log PMFs respectively. We've seen some of that. So if you do like target plus equal normal LPDF beta vertical bar 0, 1, that means independent standard normal priors on each of the elements of beta, and stand is going to add up across all k elements of beta those logarithm normal PDF terms for your prior. So normal LPDF returns a scalar that's the sum of the log prior PDFs over the k elements when you give it a vector. So the model block in this bowling case is just like 2 lines, 1 line really. All I have to do is define call bowling kernel, which is the function I defined in the functions block. And we talked about the blue thing on the right a few slides back, that returned the logarithm of the Dirichlet PDF prior plus the log likelihood for the simplex parameters that each data point on frames and pins being knocked down contributed to. So I call that function, I give it pi, I give it my vector of hyper shape parameters A, and I give it the data that came into the data block, and I just do target plus equal that, and that's my numerator in log units of Bayes' rule. I've told Stan that's my numerator, draw from this posterior distribution. So the model block implicitly is basically numerator of base rule in log units. It's a function of the parameters, but it also involves the data. And so you can refer to the data block, the transform data block. You can refer to functions that you define in the functions block. You can refer to things that you declared and defined in the transform parameters block if you need to, or other things that you declared and defined at the top of the model block if you needed some of those intermediate quantities, whatever you need to do in order to say, okay, this is what number the logarithm of base rule is in the numerator for this proposal of the parameters. In this case, we just have one set of parameters, pi. So questions about what the model block does, or its relation to any of the other blocks, or about anything else? All right. So finally, the last block is optional. It's called generated quantities. You can declare endogenous, there should be unknowns, assign to them, use them. They're going to get stored, and so they'll appear back on the R side when the jobs are finished. You can refer to anything in the previous blocks except the model block. So the model block kind of has its own scope, but in generated quantities, you can refer to things and transform parameters in parameters and transform data in data, or you can call functions that you declare in the functions block. So this is optional, and it's not strictly speaking needed because you can calculate all this stuff in R afterward once you have the draws of the parameters, but it can be used for calculating functions of interest, endogenous unknowns that you didn't need in order to evaluate the likelihood in the numerator of base rule. You can calculate posterior predictive distributions of future data or functions thereof, like your utility function that you want to maximize the expectation of. You can use it to calculate the log likelihood contribution for each of your observations, pass that to Loo afterwards. So there's a lot of things you can do in generated quantities. As an example, I calculate the posterior entropy and how much the entropy changed from prior to posterior, just more as an example of how to use the generated quantities block rather than anything that I wanted to make an inference about. But this tells me something about how much more order I've obtained in my beliefs about the parameters as a result of having conditioned on all this data about both. So it behaves more or less like transform data. It's just you can refer to parameters and transform parameters because they're, in general going to be functions of okay. So the whole STAN program, all the blocks that I've been referring to in pieces, is going to come up on the next slide, or more or less the whole thing. So one thing that you can do in STAN is specify pound include, and it's basically going to take another STAN program and just paste it in there. So my functions block, you can't actually see it, but that's because I defined it in bowling_kernel.stan, the blue thing back a few slides ago. And then data, transform data, parameters. I didn't use transform parameters, model, and generated quantities, all those little pieces that I've been talking about along the way, now all fit on one slide. And this is my entire STAN program for drawing from the posterior distribution of pi, given the data and my beliefs about the priors coming in, with some sort of extraneous stuff, but valid, going on in transform data and generated quantities that I didn't necessarily need to do, but I wanted to show examples of how all that would happen in a STAN program. Yes, Stefano.
When you say include Bowling,
when we include a function or a program from a different file, like the Bowling kernel stan, how does Stan know where to get it? Like, do we need to specify a directory or something?
So it's by default going to look in the same directory where you define the STAN program, which by default is going to be in the working directory. There is an additional argument you can give to stanc to look in another directory. So some people like to define all the functions that they use frequently in like a a directory, in which case you can specify the name of that directory to include things in. So this is just a function that downloads some data on bowling, which is surprisingly difficult to find, but basically it's like a classic homework problem in computer science to write a program that like computes the score of a bowling game. And I found this other professor who'd written a homework that had some data, which is now, I guess, a little bit outdated, from the 2010 US Open professional bowling. So I don't want to talk about this. It's just, it's formatted as a text file, and I needed to parse it in order to put it in like my 2 columns for the first roll and the second roll of each of the 10 frames. And I didn't even specifically account for the fact you can get an extra roll or 2 on the 10th frame, but just sort of, we didn't need to do that in order to understand this. So I downloaded my data. I load the RStan package. I can do each chain on a core. Not necessary in this case because it executes so quickly, but in other situations, more complicated model, bigger data sets, makes a lot of sense to use all the cores you have available. I call the stan function. I tell it the name of the main stan program that I had on the previous slide. I need to give it a named list of data. So n is the number of frames, x1, x2 is the thing I parsed on the previous slide, and I give it a vector of shape parameters from my Dirichlet prior, just 1 to 11, indicating that for professional bowling, knocking down like 9 or 10 pins is much more likely than 0 or 1. If you need to change adapt delta or max tree depth, this is how to do it, by passing a list to the control argument. But these are just the default values, and they work fine in this case, but you might need to change it. It quickly comes back with a list basically of stuff, but that includes my posterior draws, 1,000 draws after warm up on each of 4 chains with 14 parameters. And if you print it out, you get this posterior summary of the output, 1 for each of my 11 elements of pi, but also the 2 things I calculated in the generated quantities block. And this LP __ thing, which is automatically added, it contains the target value for all of the proposals and whatnot. So the logarithm of the numerator of base rule, taking into account the Jacobians in all this. So that's how you call it. And this is the basic summary of what gets out. But as usual, you can access the underlying draws, and we'll talk more about the sort of things you can do with the underlying draws on Thursday, because we're out of time for today. But that's like hello world with bowling for doing your own stan program, and it's all on Canvas. Okay, so out of time for today. Pick it up on Thursday. Continue to learn about writing simple models, but models that you couldn't just do with like VRMS or RStanArm. So I'll see you then.